Okay, here's some examples of related rates problems. Classic types of problems that you're likely to encounter. First example, sometimes they're presented in the abstract. In other words, not grounded in some kind of real physical problem. Those problems look like this. We might come across a problem in the book. There are a few of these at the beginning of section 3.7. Suppose that x and y are changing with time, just like our radius and area were with our circle, our ripple. And that the following things are true, that x squared plus 3y is equal to 5. Right? There's that relationship. Usually, like in the real problems, the real kind of word problems, this is like that thing that comes from geometry. But here, they're just giving it to us. Here's the relationship between x and y. And notice here that there are no, there's no time variable, right? This is not calculus yet. There's no derivatives in this. This is just the relationship between the actual quantities. No rates yet. And that dx dt is equal to 3 when x is equal to, let me see if I can pick a value that will make things kind of nice. Let's see. Well, I suppose it doesn't have to be nice. Let's say when it's 2, when x equals 2. Looking for no fractions in the answer, but can't spot an x that'll do that right now. And now they want us to find the rate that y is changing when x is 2. All right, so let's go back to our 4 steps here, see how this applies. Well, this isn't a real like word problem kind of thing, so I think the drawing a picture doesn't really apply here. Find a relationship between the variables and known quantities, and here they gave us that relationship. So we're really going to bypass steps 1 and 2 and go straight to step 3. Take the derivative of this equation with respect to time. So now listen, if we were just taking a regular derivative, we know the derivative of x squared is 2x. But we're taking the derivative now with respect to time. So every variable that we hit, a d whatever, in this case dx, dt, is going to pop out. Why does it pop out? I understand it as being just a manifestation of or an example of the chain rule, right? The derivative of what's inside. Well, if it was x, if x was the variable here that we were taking the derivative with respect to, if it was a dx problem, this would be dx, or just 1, right? But here, it's time we're interested in. So, even with an x, that pops out. Now, what's the derivative of 3y? The derivative of y is dy dt, right? Understand here, this was x squared, so it was 2x dy dt. This is just 3y to the first power, so that's just 3 times the dy dt that pops out. And then here, what's the derivative of 5? The derivative of 5 is 0. There is no variable there. So be careful. That's a common mistake in this kind of problem. You got a constant all by itself here, that's going to go to 0 when you take the derivative. Okay, now we're supposed to plug in what we know. So let's see if we can do that. So 2, we're talking about when x equals 2, so x is 2, and they told us, or I told you, what dx dt is. That's 3 plus 3 times dy dt equals 0. And that looks good. We've got an equation only with one variable in it here. Oh, and it did turn out to be nice after all. So dy dt, or I'll do it in a couple steps here. This is 12. We'll subtract that over to the other side, doing some reassuring algebra 1 at this point. So dy dt is -4. That's what they asked us for, find dy dt. All right, what does all that mean? It means that if this is in fact the relationship between x and y, and if in fact the x value is changing at 3, we don't have any units, but like 3 units per second or whatever our time units are. It just said dx dt is 3 when x is 2. If that's all true, then the y value must be changing at -4 units per time, right? Units per second or whatever. And if you wanted to actually, I didn't do this on purpose, but this turns out just to be a parabola, right? You can move the x squared to the other side. What this means is that if something were moving along this parabola, and the x value were changing this much at this point, this is how much the y value would have to be changing at that same point. That's all very abstract. So, you plug in the values, you follow the procedure, and you get that. Let's do another problem that's a little bit more physical. So we'll do one. Here's another classic problem, the falling ladder. So let's say we've got, here's the ground, here's like a house or something like that. We've got a ladder that's leaning up against the side of this house. And let's say the ladder is 10 feet. This is a 10-foot ladder. And let's say, we'll call this example 2. Let's say that the top of the ladder is falling at 2 feet per second. Right? So the ladder is slipping, it's sliding down the wall, and the top of it here is descending at 2 feet per second. Okay? And I'd like to know how fast is the foot, this we'll call this the foot of the ladder, is the foot of the ladder moving, when it is 6 feet from the house, or the wall, whatever that is, in the house. Okay, well, let's look at our steps here. So draw a picture. Well, I drew it. Often the picture comes with the problem. So I drew it, but I don't think I've labeled everything yet, so I think we should do that first. So let's see, what do we know? The top of the ladder is falling at 2 feet per second. Well, I did label that in here, right? And we know that it's a 10-foot ladder. I've got that in there. How fast is the foot of the ladder moving? So I want to know how fast that's moving. Don't know that right now, but we're looking for it. And when the foot is 6 feet from the house, so this right now is 6 feet from the house. Well, let's label these things. This is a variable, right? Let's call it, since it's horizontal, I'll call that x. And this is variable, right? How high the ladder is. Like those are both going to change. Like if this were the ladder, it's kind of sliding. Ooh, that's good. Look at that, right length. So it's like sliding like this, right? Slipping down like that. And so this is changing, this x is changing, and this y is changing. Well, anything that's changing, that means it's also got a rate with it, right? What's the rate of this? Well, it's dx dt. What's the rate for the y? It's dy dt, right? So let's see if we know anything else here. I think we know this rate, right? dy dt. It's 2, but be careful because it's falling. That y value is getting smaller. So the falling here is tipping us off that this needs to be -2 feet per second. Right, that's falling. And do I know what y is? Well, actually, yeah, at this like snapshot, at this frozen instant in time, the 10-foot ladder, of course, that's not variable, right? The ladder is the same length. That's not changing, so I don't need to make that like z or something. It's just 10. But this is a 6, 8, 10 right triangle. You could use the Pythagorean theorem if you didn't spot that. But since I know two sides of the triangle, I can use the Pythagorean theorem to find the other side. And, well, hey, I guess that's our relationship now, isn't it? What's the relationship between... Now, here, I'm not looking at the rates, right? That's calculus. I'm not looking for calculus yet. I'm looking for geometry. This is a right triangle, and we're looking for a relationship between our variables and known quantities. So what is that relationship? It's the Pythagorean theorem. We got a right triangle, and we got a bunch of sides. So this side, which is variable, plus this side squared, also variable, is equal to this side squared. And this side is not variable. It's always 10, so I don't need to make it a variable here. Okay. So there's my equation from geometry. That was step 2. As advertised, Pythagorean theorem is sometimes the relationship. Okay, now we need to take the derivative of that equation with respect to time. The derivative of something squared is 2 times that something times the derivative, or its rate, which is dx dt. Remember, every single letter that you take the derivative of, that's going to pop out. Plus, derivative of y squared is 2y dy dt. And the derivative of 10 squared is not 2 times 10. This 10 squared is just 100. That's a number. Its derivative is 0. All right, let's see if we can plug stuff in and get our answer here. So 2 times the x value, which at this moment in time is 6, times dx dt is what we're looking for, right? How fast the foot's moving. That is dx dt, plus 2 times the y value is 8, times dy dt is -2, equals 0. And there we go. Back to Algebra 1. So 12 dx dt. Imagine Algebra 1 students would get very frightened if they saw something like that, though. Of course, we're just solving for that, so no big deal. Minus 4 times 8 is 32, equals 0. So dx dt is equal to 32 divided by 12, and 4 goes into both of those, so I suppose we can dutifully reduce that to 8/3. And listen, in a word problem like this, fractions aren't usually so appropriate as answers, so maybe we want to actually make that 2.67, something like that, feet per second. So when the top is falling at 2 feet per second, the bottom is moving away from the house at 2.67 feet per second. Now, if your intuition wanted to tell you that those two numbers should be the same, then you might think about like the extreme ends of this. Like if the ladder were way, like almost to the ground, this moving a little bit here makes a much bigger difference here. Right? So these two things are not going to be the same. Those two rates are not the same. There's a relationship between the rates. It's this. This is the relationship between the rates. This is a related rates problem. And oh, by the way, if you're very good with your units, you might notice that since this is 2/3 of a foot, that's 2/3 and 8 inches per second. If you want to get some brownie points there. All right, give you one more example. This is another classic one. I've seen this one come up on the AP test a couple times. Say we've got a cone. That's being filled with water. And the radius of the cone is 5 centimeters. It's like one of those little water cooler cups, right? And the height of the cone is 10 centimeters. And there's the water going in, right? So it's something like that. Well, I think if you think about this problem for a minute, when you turn the water cooler on or you open up the little valve and water starts coming in, it comes in at a constant rate, right? So we might know, for example, if we had measured that flow rate, that water is coming in at, let's say 5, what would the units be? Think about this. This is the rate that water is coming in. It would have to be volume, right? Water that's taking up some space, so maybe 5 cubic centimeters per second. Something like that. Now, there you go. That's a rate. So what is this? Maybe it's worth thinking about that right now. What is this? This is the rate that the volume is changing with respect to time. So you got to be on your toes here. They've given us a rate, so we have to figure out what rate it is. Nobody's going to tell you, like dV dt, well, sometimes they do, but here, it was given in words here, and we had to interpret that. Oh yeah, that's dV dt. All right. Now, we got our picture here. Oh, and we need a question. So we want to know how fast is the height of the water, right? Or you guys could say the depth of the water. Maybe that would be more sensible way to say it. But that's height, same thing, right? How fast is the depth changing when, sorry, it's getting late, when the depth is, let's say halfway up, is 5 centimeters. All right, well, we want to know particularly when h is equal to 5 centimeters. That would be the h, right? That's the instant in time, that like snapshot in time that we're interested in. And, well, let's go on for a second. And what's the relationship from geometry? Well, we've got volume of a cone. We know we're talking about volume here. We've got that rate. So you might have to look this up. I don't know if you remember this formula. The volume of a cone is 1/3 pi r squared h. I don't know if you have to memorize that formula or not, but it does come up. This is a classic related rates problem, so tuck that away if you have any available space in your memory. But you might be given it if you needed it. Okay, now the problem is here. We could go ahead to step 3, take the derivative of this equation, but there's 2 variables over here, and that is going to get pretty nasty because I'm going to have to do the product rule there, and I would rather not do that. So is there any way I can eliminate one of those variables? The answer is yes, because no matter how deep this cone is. Like imagine this is the height of the cone. Wherever you cut it off here, you always have a similar triangle to the original 5-10 triangle. That means that, in other words, the radius to the height is always 5 to 10, right? The radius is half the height. Well, that's always going to be true. When we're here or when we're here, the radius is always going to be half the height. So let me just solve here for r. That means r is equal to 1/2 h, right? That's just a little bit of algebra on that. And using this fact, I can substitute here. And really, since we're interested in depth, we're really only interested in h's anyway, so it serves me perfectly well to get rid of the r's. So let's do that. So v is equal to 1/3 pi. R is equal to 1/2 h, right? So I'm substituting that in there. Okay, all I did was take this, put it in place of the r. And let's see, 1/2 squared is 1/4 times 1/3 is 1/12 of a pi times h cubed. Well, that's better. Let me just rewrite that. So volume equals pi over 12 times h cubed. Now we're ready for step 3. Now we can take the derivative of this equation. What's the derivative of v? dv dt. And then the derivative of h cubed is 3, so 3 times pi over 12 is pi over 4, right? 3 over 12 is the same as 1/4. H squared, that's just using the power rule on this, times dh dt. And if you accidentally forgot that, your clue that you missed something is, we're looking for how fast is the depth changing. Well, that's a dh dt, so you better have a dh dt in your equation here. You're not going to be able to solve for it. Okay, so now we're almost home free. So here, dv dt is 5. That's equal to pi over 4 times the height, depth, height, same thing, 5 squared times dh dt. And now we just need to solve for dh dt. I'm not going to get my calculator out and find the decimal answer, but it looks like we would have, let's see, that would be, this would flip over on the other side, right? So that'd be 5 times 4 over pi, and then the 5 squared would end up on the bottom here, something like that. Well, the 5's cancel, so it looks like it's 4 over 5 pi. And I will tell you, because I've seen this mistake so many times and I don't want you to make it, when you enter this in your calculator, you need to enter 4 over, in parentheses, 5 pi. That will give you the correct answer. If you enter 4 over 5 pi, your calculator thinks that you're doing 4 over 5 times pi. That's the same as 4 pi over 5, not 4 over 5 pi. So this, incorrect. And don't just go thinking that one set of parentheses will solve all your problems. That's the same as this. That's also no good. You have to have the whole bottom of the fraction in parentheses. And the funny thing is that if you accidentally divide by pi instead of multiplying by pi, or vice versa, because it's a factor of approximately 3 on the top and a little bit more than 3 on the bottom, it makes your answer look like it was right, but you missed the decimal point by 1 place. And actually, I will take a second to show you that. So check out what the two answers look like. If you do the correct answer, 4 divided by 5 pi, oops, what's that doing there? You get 0.255. Remember, we're going to always round to 3 decimal places. And units here would be, since we're talking about the height changing, that would be centimeters per second. But if you do 4 over 5 pi, look at that, you get 2.51. So you might think to yourself, oh, I just missed the decimal point, but it's not, it has nothing to do with that. It's just because the multiplying and dividing, you're basically off by a factor of pi squared, which is almost 10. Right? So there you go. All right, that's probably a little bit too long for one video, 25 minutes, but there's a lot there for you to look at. Good luck.